electricity in the automobile. In the past, electrical systems were basically standalone. For example, the ignition system was only responsible for supplying the voltage needed to fire the spark plugs. Ignition timing was controlled by a vacuum and the mechanical advanced systems. Today, there are very few electrical systems that are still independent. Today, most manufacturers network their electrical systems together through computers. This means that information gathered by one system can be used by another. The result might be that a faulty component may cause several symptoms. Consider the following example. The wiper system can interact with the hill light system to turn on the highlights whenever the wipers are turned on. The wipers can interact with the vehicle speed sensors to provide for speed-sensitive wiper information. The speed sensor might provide information to the anti-lock brake module. The anti-lock brake module can then share this information with the transmission control module. And the instrument cluster can receive vehicle speed information to operate the speedometer. If the vehicle speed sensor should fail, this could result in no anti-lock brake operation and the warning light turned on into the dash. But it could also result in the speedometer not functioning, the transmission not shifting, and the wipers not operating. One of the most amazing things about electricity is that it is literally everywhere. But that I don't mean the electricity is commonplace or plentiful, or even that universe has abundant supply of electricity. Instead, what I mean is that electricity is a fundamental part of everything. To get an idea of what I mean, consider a common misconception about electric current. Most of us think that wires carry electricity from place to place. When we plug in a vacuum cleaner and turn on the switch, we believe that electricity enters the vacuum cleaner's power cord at the electrical outlet, travels through the wire to vacuum cleaner, and then turns the motor to make the vacuum cleaner suck up dirt and grime and dog hair. But that's not the case. The truth is that electricity was already in the wire. The electricity is always in the wire, even when the vacuum cleaner is turned off or the power cord is not plugged in. That's because electricity is a fundamental part of copper atoms that make up the wire inside the power cord. Electricity is also a fundamental part of the atoms that make up the rubber insulation that protects you from being electrocuted when you touch the power cord. And it's fundamental part of the atoms that make up the tips of your finger, which the rubber keeps from touching the alternating current, abbreviation AC, flow of the electric charge that periodically reverses. It starts, say, from 0, grows to maximum, decreases to 0, reverses, reaches a maximum in the opposite direction, returns again to the original value, and repeats this cycle indefinitely. The interval of the time between attainment of a definite value on two successive cycles is called the period. The number of cycles or periods per second is the frequency, and the maximum value in either direction is the amplitude of the alternating current. Low frequencies, such as 50 or 60 cycles per second Hertz, are used for domestic and commercial power. But alternating currents of frequencies around 100,000 billion cycles per second, which is 100 megahertz, are used in television and use of several thousand megahertz in radar or microwave communication. Cellular telephones operate at frequencies of about 1000 megahertz. 1000 megahertz is equals 1 gigahertz. Alternating current AC has a distinct advantage over direct current DC of being able to transmit power over large distances without great loss of energy to resistance. The power transmitted is equal to the current times the voltage. However, the power is lost is equal to resistance times the square of the current. Changing voltages was very difficult with the first DC electric power grids in the late 19th century. Because of the power loss, these grids used low voltages to maintain current and could only transmit usable power over short distances. DC power transmission was soon supplanted by AC systems that transmit power at very high voltage and correspondingly low current, and easily use transformers to change the voltage. Current systems transmit power from generators at hundreds of thousands of volts and use transformers to lower the voltage to 212 volt or 220 volt. As in much of the world, or 120 volt in North America for individual customers. The DC, direct current, is the one-directional flow of electric charge. An electrochemical cell is prime example of DC power. Direct current may flow through the conductor such as a wire, but can also flow through semiconductors, insulators, or even to the vacuum as in electron or ion beams. The electric current flows in a constant direction, distinguishing it from alternating current AC. A term formerly used for this type of current was galvanic current. The abbreviations AC and DC are often used to mean simply alternating a direct, as when they modify current or voltage. Direct current may be converted from an alternating current supply by use of rectifier, which contains electronic elements or electromechanical elements that allows current to flow only in one direction. Direct current may be converted into alternating current via an inverter. Direct current has many uses, from the charging of batteries to large power supplies for electronic systems, motors, and more. Very large quantities of electrical energy provided via direct current are used in melting of aluminum and other electrochemical processes. It is also used for some railways, especially in urban areas. High voltage direct current is used to transmit large amounts of power from remote generation sites or to interconnect alternating current power grids. The difference between alternate and direct current. An electric current that flows through consistently in a single direction is called a direct current, or DC. The electrons in wire carrying direct current will move slowly, but eventually they travel from one end of the wire to the other because they keep plodding along in the same direction. The voltage in a direct current circuit must be constant, or at least relatively constant to keep the current flowing in a single direction. Thus, the voltage provided by a flashlight battery remains steady at about 1.5 volt. The positive end of the battery is always positive relative to the negative end, and the negative end of the battery is always negative relative to the positive end. This constancy is what pushes the electron in a single direction. Another common type of current is called alternating current, AC. In an alternating current circuit, voltage periodically reverses itself. When the voltage reverses, so does the direction of the current flow in the most common form of alternating current, used in most power distribution systems throughout the world. The voltage reverses itself either 50 or 60 times per second, depending on the country. In the United States, the voltage is reversed 60 times per second. Alternating current is used in nearly all the world's power distribution systems. For the simple reason, the AC current is much more efficient when it's transmitted through the wires over long distances. All electronic current lose power when they flow for long distances, but AC circuits lose much less power than DC circuits. The electronic in an AC circuit don't really move along with the current flow. Instead, they are sort of sit and wiggle back and forth. They move one direction for 60 times of seconds and then turns around and go to the other direction for 60 times of a second. The net effect is that they don't really go anywhere. System of units defines the ampere in terms of the base units by measuring the electromagnetic force between electrical conductors carrying electrical current. The earlier ZGS system had two different definitions of current, one essentially the same as the SCEs and the others using electrical charge as the base unit, with the unit of charge defined by measuring the force between two charged metal plates. The ampere was defined as 1 coulomb of charge per second. The unit of charge, the coulomb, is defined as the charge carried by 1 ampere during 1 second and isolators. Some elements don't hold on their outermost electrons very tightly. These elements frequently lose electrons or pick up extra electrons, and so they frequently get bumped off of neutral and become either negatively or positively charged. Such elements are called conductors. The best conductors are the metal silvers, copper, and aluminum. Other elements hold onto their electrons tightly. In these elements, it's hard to pry loose an electron, force another electron in. These elements almost always stay neutral. They are called insulators. In a conductor, electrons are constantly skipping around between nearby atoms. An electron jumps out of one atom called atom A into nearby atom, which I will call atom B. This creates a net positive charge in atom A and a net negative charge in atom B. But almost immediately, an electron will jump out for a nearby atom, call it atom C, into atom A. This atom A again becomes neutral, and now atom C is a negative. This skipping around of electrons in a conductor happens constantly. Atoms are perpetually terminal, giving and received electrons and constantly cycling their net charge from positive to neutral to negative and back and positive. Originally, this movement of electrons is completely random. One electron might jump left, but another jumps right. One goes up, one another goes down, one goes east, the other goes west. The net effect is that all the electrons are moving. Collectively, they aren't going anywhere. They are like keystone cups, running around aimlessly in every direction, bumping into each other, falling down, picking themselves back up, and they running around some more. When this randomness stops and the keystone cups get organized, the result is electrical current. Electric current. Electric current is what happens when the random exchange of electrons that occurs constantly in a conductor becomes organized and begins to move in the same direction. When current flows through a conductor, such as a copper wire, all those electrons that were previously moving about randomly get together and start moving in the same direction. A very interesting effect that happens. There are electrons transfer their electromagnetic force through the wire almost instantaneously. The electrons themselves all move relatively slow, on the order of a few millimeters a second. But as each electron leaves an atom and joins another atom, the second atom immediately loses an electron to the third atom, which immediately loses an electron to the fourth atom, and so on trillions upon trillions of times. The result is that even though the individual electrons move slowly, the current itself moves at nearly the speed of light. Thus, when you flip a light switch, the light turns on immediately, no matter how much distance separates the light switch from the light. It's no coincidence that moving wire is called current. Many of the early scientists who explored the nature of electricity believed that electricity was a type of fluid, and that is flowed in wires in much the same way that water flows in a rock. In its natural state, the electrons in a conductor such as copper freely move from atom to atom, but in a completely random way. To get them to move together in one direction, all you have to do is give them a push. The technical term of this push is electromotive force, abbreviated AEMT, or sometimes simply E, but you know it's more common as voltage. A voltage is nothing more than a difference in charge between two places. For example, suppose you have a small clump of metal whose atoms have an abundance of negatively charged atoms and another clump of metal whose atoms have abundance of positively charged atoms. In other words, the first clump has too many electrons and the second clump has too few. A voltage exists between these two clumps. If you connect those two clumps with a conductor such as copper wire, you create what is called circuit, through which electric current will flow. The current continues the flow until all the extra negative charge on the negative side of the circuit has moved to the positive side. When that has happened, both sides of the circuit become electrically neutral and the current stops flowing. Whenever there is a difference in charge between two locations, there is possibility that the current will flow between two locations if these locations are connected by a conductor. Because of this possibility, the term potential is often used to describe voltage. Without voltage, there can be no current. Thus, voltage creates the potential of current to flow. If current can be compared to the flow of water through the hose, voltage can be compared to water pressure at the free suit. It's water pressure that causes the water to flow in the hose. If the current can be compared to the flow of the water through the hose, voltage can be compared to water pressure at the expansion. It's water pressure that causes the water flow in the hose. Power is the work done by an electrical circuit. Electric current in and of itself isn't all that useful. It becomes useful only when the energy carried by an electric current is converted into some other form of energy, such as heat, light, sound, or radio waves. For example, in an incandescent light bulb, voltage passes current through a filament, which converts the energy carried by the current into heat and light. Power is measured in units called watts, abbreviated W. This definition of 1 watt is simple. 1 watt is the amount of work done by a circuit in which 1 ampere of circuit is driven by 1 volt. The relationship lends itself to simple equation